Hello students, after the relation, function and kinds of function and composition of function, we have one important topic here, inverse of function. How will you find the inverse of function? Before this, we have to discuss about inverse of an element. In a function, how how you find the value inverse of an element? Let f mass from A to B is a function we can see from the Venn diagram. This is set A and this is set B, and f function is defined on set A to set B, where A set is domain set and B set is codomain set, and the one element x belongs in A associated to the y under f function which belongs in set B. Then you can write as y is equals to fx, means y is image of x. Y is image of x. It means you can write as y is equal to fx. Y is image of x under mapping of f. The meaning of this is, in other word, we can write as this element x is said to be pre-image of y. X is pre-image of y. The pre-image of any element is said to be inverse element. The pre-image element is said to be inverse element of the corresponding image in the codomain set. In other words, we can write as x is pre-image or inverse element of y under function f, that is x is equal to f inverse y. This represents that x is inverse element of y under the function f. In notation we have to write as x is equal to f inverse y. Let an example, f is a function which maps from the set A to set B such that in set A there are elements a1, a2, a3, a4, and in set B, b1, b2, b3, b4 and b5 are the elements. F is mapping which starts from set A to set B, then set A will be domain set and B is codomain set. A is domain set and B is codomain set. A1 is associated to B1, A2 is associated to B1, A3 is associated to B4 and A4 is associated to B5. These are pre-images of the elements B1, B4 and B5. Only the element B1, B4 and B5 are associated to the element of set A under the f function. So range of this function will be b1, b4, b5, because the definition of range is the collection of all pre-images b1, b4, b5. And remember the kinds of function. Which type of function this is the function 1 1, is the function onto. First we have to check for and 1 1. Every distinct element have distinct images in the function is said to be 1 1. Here two different elements a1, a2 have same images in the set B, so it is not 1 1 functions, it is on many one, it is said to be many one. If a function is not 1 1, then it will be many one. It means a pre-image have more than one image pre-images in domain set, then the function is said to be many one function. So it is many one function. Now check for onto function. The definition of onto function is every element of codomain set, this is the codomain set, have images, unique images in domain set. Here see, b2 and b3 have no images, pre-images in domain set, not association here, so this is not onto. If a function is not onto, so it is, in that case we can say into function. Okay, now our topic is inverse of an element. We have to find the inverse of element. Just for a revision, I do from above function, inverse of element. Inverse of b1 element is a1. Inverse element is pre-images, like pre-images of b1 is a1. You can write as inverse of b1, f inverse b1 is equals to a1. b1 is also associated to the element a2, f inverse b1 is a2. b4 is associated to a3, f inverse b4 equals to a3. f inverse b5 equals to a4. These are the inverse element of the corresponding elements. Now second example, let f is a function which maps from x to y. X is domain set and y is codomain set, such that here given this is x set and y is set. Here x1, x2, x3, x4 are the elements of set x, and y1, y2, y3, y4 are the elements of set y. And this is association. This represents the association of the element of set x to set y. Now see which type of function this is. 1 1 onto. Check for 1 1. Every different element have different images in y, so it is 1 1 onto. For 1 2, check every element of codomain set is associated to the element of domain set, so it is onto also. This is 1 1 and onto function. If a function is 1 1 and onto, then it is called bijective function. Okay, we have to find here the inverse of every element of codomain, which is association is given. Now inverse element are f inverse y1. y1 is associated to x1. Pre-images of y1 is x1, so f inverse y1 is equals to x1. f inverse y2 is equals to x2. f inverse y3 is equals to x3. f inverse y4 is equals to x4. These are the inverse element. Now see the instruments in both the examples. This is not 1 1 not on 2, and this is 1 1 and onto function. Now see, is it possible here a function from y to x, any function from y to x, is it possible? Now remember the definition of the function. The definition of the function is every element of a set associated uniquely to the element of another set, then it is said to be function. Here association of element of y, if we take this is domain set and this is codomain set. Now see, every element is associated to the element of set x uniquely, so a function is possible from y to x also. A function is possible from y to x because it is 1 1 and onto. If a function is not 1 1 and onto, in that case is it possible from one set to another set? Function from one set to another set. Now check here in the first example, this is not 1 1 not onto. If we make this domain set, this is domain set, is it possible from a function from b set to a set? Now apply the definition of the function and check here. For the function, every element of set b is associated to the element of set a, but here b2 and b3 is not associated to the element of set a, so it will not be function. If association of elements b2 and b3 is possible, means it is onto, in that case it will not possible, because b1 have two images in the function. Every element have unique images, only one image. But in the many one function is given, in that case the inverse function is not possible, because for the function every element should have only one images. So if a function is 1 1 and onto, if a function is 1 1 and onto, then in that case inverse function means from codomain to domain also a function is possible. If a function is many one or not onto, in that case a function b to a means inverse function is not possible. Now the students, after the inverse of element, our next topic is inverse of a function. The definition of the inverse of a function is: let f mass from a to b be a bijection. Bijection means if a function is 1 1 and onto, then the function is said to be 1 1 onto or bijection. So now we have a function f mass from a to b which is bijection, then a function g mass from b to a which associates each element y belongs in b to a unique element x belongs in a, such that fx equals to y is called the inverse of f. That is fx equals to y. Now you can understand by this Venn diagram. This is set A and this is set B. F is a function which maps from set A to set B. Let one element x in set A and y belongs in set B. X is associated to the element y under f function. Then fx we can write as fx is equal to y. Fx equals to y. And we have another function g which maps from b to a, f maps from a to b, and g another function which maps from b to a. You can consider as this function. This is g function which maps from b to a, such that gy, this y element associated to the element x under g function gy, then you can write gy is equals to x, means fx equals to y and gy equals to x. X associated to the element y and y associated to x. It means g will be inverse function of f. G will be inverse function of f, because invertly y associated to x, x associated to y, and invertly y associated to x. So g is called inverse of f. It means we can write as if f maps from a to b, this is a bijective function, means 1 1 and onto function, then inverse of f, inverse function of f inverse which maps from b to a. This is domain set and codomain set of for the function f, and for the function f inverse this will be domain set and this will be codomain set. So f inverse maps from b to a, such that fx is equals to y, then f inverse y is equals to x, because y is inversely associated to x. This is the inverse function. And here algorithm to find the inverse of a function. How will you find the inverse of a function, and what is criteria to find the inverse of function? Let f maps from a to b be a bijective function. Bijection, it means 1 1 function. every bijective function is an invertible function. It means we can find inverse of only bijective function, means that function which are 1 1 and on 2, then the function uh, be invertible, will be invertible. Here first step is put fx is equals to y, where y belongs in B. Fx is equals to y, this y belongs in B. See here, fx is equals to y belongs in B, and x belongs in set A, this x belongs in set A. Okay, so first we have to write fx is equals to y, solve fx is equals to y. We have to solve this statement fx is equals to y, and we have to find the value of x in terms of y. We have to obtain x in terms of y. In the third step, we have to replace x by f inverse y in the second step. When we get the value of x in terms of y, then x we have to replace this x by f inverse y. Finally, you get the inverse of f. After the definition of the inverse function and the steps of the to find the inverse of a function, we have one example by which you can understand very well. This example is, let f is a function which maps from R to R. R is a set of the real number, and this R is also set of real number, be defined by fx is equals to 3x minus 7. Show that f is invertible. First of all, we have to show this f is invertible, and hence find f inverse. First of all, we have to show here f is invertible. Remember the definition of the inverse function and criteria of inverse function. Every bijective function is invertible. It means, first of all, we have to show f is bijective function. It means to show f is invertible, it is sufficient to show that f is bijective function. Bijective means a function is 1 1 and on 2. Then we have to show f is two types of function. First is 1 1 and then on 2. Now start the solution. To show f is invertible, it is sufficient to show f is 1 1 and on 2. First we have to prove to check for 1 1. How do you check for 1 1? If a function f r to r, this is given that f maps from R to R, let two elements x1 x2 belongs in domain set this R. Let x1 x2 belongs in R such that fx1 is equals to fx2. Now find the value of fx1. The given fx is equals to 3x minus 7, then fx1 is equals to 3x1 minus 7, and fx2. How will you find the value of fx2? Substitute the value of x x equals to x2, in this function 3x2 minus 7. fx1 is equals to fx2. Now substitute here. This will be 3x1 minus 7 is equals to 3x2 minus 7. By the cancellation law, minus 7 will be cancelled. Then you will get 3x1 is equals to 3x2, and this 3 cancel. It means x1 is equals to x2 for all x1 x2 belongs in theta. Okay, so the function will be 1 1. Now check for on 2. If a function is on 2, how is check? Now put fx is equals to y, fx equals to y, where y belongs in codomain set and x belongs in domain set. Here both domain and codomain both sets are R, because f maps from R to R. The given function fx is equals to 3x minus 7. Now substitute here, and y. Solve for x. Now x will be equals to minus 7 transfer in right side. This will be y plus 7, and 3 divide in here, y plus 7. Then you will get x equals to y plus 7 upon 3, where x belongs in real number and y also belongs in real number. Now check for every y belongs in real number. Is it possible x belongs in real number? For all y belongs in real number, x is equals to y plus 7 upon 3 belongs in real number. If we put here any real number at place of y, after solving you will get a real number. If we put here y equals to 1, then you will get 8 upon 3. Y is equals to 0, then you will get 7 upon 3. If y is equals to root 2, then 7 plus root 2 upon 3. This is also a real number. If we put at place of y any real number, then you will get another real number x, which belongs in R. So this implies f is on 2. It means f is 1 1 and on 2, so it is bijective. Hence f is invertible. Now inverse of f. Follow the algorithm to find the inverse of f. First of all, we have to put fx equals to y. Here given fx is equals to 3x minus 7. Now substitute fx is equals to y here. Then y will be equal to 3x minus 7. Okay. From this step, we have to find the value of x in terms of y. X will be equal to y plus 7 divided by 3, because minus 7 transfer in left side, y plus 7, and 3 divide y plus 7 upon 3. In this step, we have to write at place of x f inverse y, as we discussed in the algorithm. This is the third step. We have to write f inverse y at place of x. This is the inverse function of f. Here few properties related to inverse of a function. The first is the inverse of a bijection is unique. It means every bijective function has unique inverse function. Means we have only one inverse function of a bijective function. How do you prove this? Let f maps from a to b be a bijection. Bijection means bijective function. f is a bijective function, it means f is one function and onto function. It means one function. One function means in the domain set A, every distinct element have distinct images. Onto means every element of codomain set should be associated to the domain element. F is one and onto it is given. If possible, let another function g which maps from B to A and h maps from B to A. We have to consider two functions g and h which maps from B to A and B to A also, because we have to prove here inverse of bijective function is unique. Then we have to consider two functions g and h which are inverse of f. First we have to consider f as f have two inverse function, and last we have to show g and h both are equal function. Okay, now start. Let g maps from B to A and h maps from B to A be two inverse function of f. Then we have to prove that g function and h function both are equal. In order to prove this, it is sufficient to show that gy is equals to hy. If two functions are equal, then image of a point, any element under the both functions will be equal. It means y is an element in domain, y belongs in B. B set is domain set of g function and h functions also. Y is an element in this set B. Then association of y should be equal in both functions, gy equals to hy. Let y belongs in B. Suppose gy is equals to x1 and hy equals to x2. We have to consider y is associated to x1 under g function and y is associated to x2 under h function. Gy equals to x1 and fx1 equals, so you can write fx1 is equals to y because g is inverse of f. We already considered it. Gy is equals to x1. This implies fx1 is equals to y because f is inverse function. Hy equals to x2. Then you can write fx2 is equals to y because f is also inverse of h. H is inverse of f. Okay. Here fx1 is equals to y, fx2 equals to y. It means therefore fx1 is equals to fx2. Fx1 equals to y and fx2 equals to y is therefore fx1 equals to fx2. This implies x1 equals to x2. Since f is one function, because f is one and onto function, it is given here f is bijective function. If f is bijective function, it means it will be one function. For the one function fx1 equals to fx2, so x1 equals to x2. The value of x1 is gy and x2 is hy. Now substitute here gy and hy. It means gy and hy both are equal. It means g function and h are both will be equal. Now we have second theorem related to the inverse of a function. If f maps from A to B and g another function which maps from B to C are two bijections, means both functions are one and onto, then g of f means composition of function g and f which maps from A to C is a bijective function, and g of f inverse is equal to f inverse of g inverse. This theorem is very important for the board exam. Okay, now start the proof of this theorem. Now say in this Venn diagram. F function is given which map from set A to set B, and G is another function which map from B to C. B to C. F function and G function both are one function. It means every distinct element have distinct images in here, and F is onto here. It means onto means every element of B set should be associated under F, and G is also 1 means every distinct element associated to distinct element in set C, and G is also onto, it means every element of C set is associated under G. Now we will get another function from A to C. This is G of F. This is the composed function of F, G function and F function. Now start proving. We have F map from A to B, which is a bijective function, and G is also a bijective function which maps from B to C. Then you will get G of F. As we discussed in composition of function, composition of bijective function is also a bijective function. So F function and G function both are bijective function, then their composition is also bijective. It means G of F is also bijective because F have different elements. It means few elements like this, F in B and in C. F is associated to this element, G this element, this is associated to this element, and this is associated to this element, and this element is also associated to this element, and this element is associated to this element. Okay, you can understand that by this. Okay, now see in composition from A to C, this element is associated to this element, this element is associated to this element, this is associated to this element, this element is associated to this element via these elements. Okay, it means this function from A to C is 1 because every distinct element have distinct images, and every element of this set is associated under this function from A to C. So G of F from A to C is also a bijective function. If a function is a bijective, so its inverse exists, as we discussed in the definition of inverse function. Every invertible function is bijective function, means every bijective function possesses inverse of itself. G of F inverse which map from C to A. If G of F maps from A to C, then inverse of G of F maps from C to A. Now F maps from A to B is a bijective function. If F A to B, F is a function which maps from A to B, then its inverse maps from B to A. G is a bijective function, so its inverse exists, which its inverse maps from C to B. G inverse maps from C to B. It is also bijective function. Again, apply the theorem property of the composition of two functions. F inverse, G inverse both are bijective functions, so its composition is also bijective. F inverse of G inverse. See carefully, G inverse, this is G function which maps from B to C, its inverse maps from C to B, it means G inverse maps from C to B, and F inverse maps from B to A, F maps from inverse maps from B to A. So composition of from C to A, the function will be F inverse of G inverse because F inverse this function and G inverse this function. Then composition from C to A will be F inverse of G inverse. Let X belongs in A. X is an element which belongs in A, and Y belongs in B, and Z belongs in C. If any element X belongs in set A and Y belongs in set B, and z belongs in set C, then you can write fx is equals to y, because this is inverse function. Then f maps from a to b, then fx is equals to y, and gy is equals to z. Now find the value of g of fx. To find the g of fx, we have to break this. You can write as g of fx, and we have fx equals to y. Now substitute here the value of fx. This is y, gy, and the value of gy is z. Means g of x is an element which belongs in set A, and this will be associated to the element z. Means g of fx is equals to z. Then inverse of g of f inverse x z associated to the element x. Now fx equals to y and gy equals to z. Fx equals to y and gy equals to z. If fx equals to y, then you can write f inverse y is equals to x, and gy equals to z, then you can write g inverse z equals to y. Now composition of these two functions, f inverse of g inverse. Here z is an element, then you can write f inverse g inverse z. G inverse z equals to y. Now substitute here y. F inverse y is equals to x, means f inverse of g inverse z equals to x. This is equation 2 and this is equation 1. From equation 1 and 2, g of f inverse z equals to x and f inverse of g inverse z is equals to x. Both are equal. Now equate. After equating from equation 1 and 2, g of f inverse z equals to f inverse of g inverse z. Finally you will get both functions are equal. It means g of f inverse is equals to f inverse of g inverse. Now hence proved. Now we have the next theorem. This is third theorem. This is also very important. Let f maps from a to b be an invertible function. If f function is invertible function, it will be bijective, means 1 1 and on to show that inverse of f inverse is f. Inverse of f inverse is also a function, means inverse of this function is f, that is f inverse equals to f. Now say f maps from a to b. This is invertible function. Then its inverse exists, which maps from f inverse maps from b to a. This is inverse of f function. Now see in this Venn diagram, f is a function which maps from a to b and its inverse maps from b to a. After composing these two functions f and f inverse, then you will get f inverse of f, which maps from a to a. A to a, it means then you will get identity function ia. After composing two functions f and f inverse, this will be f inverse of f, then you will get identity function ia, because this function composition function is defined on the same set. This will be identity function. And now compose two functions f inverse and f like this. As we discussed above, f inverse maps from b to a and f function maps from a to b. Now composing these two functions f and f inverse, this will be f of f inverse, which maps from this b set to b set. Composition of functions from same set to same set, then it will be identity function. It means f of f inverse will be equals to ib. You can write. Now see, you can write as f inverse of f equals to ia from here, and f in composition of f and f inverse will be ib. Both are identity functions. It means after composition of two functions, you get an identity function. In that case, one function will be inverse of another function. It means f will be inverse of this function. You can write, means f is inverse of f inverse. this function f will be inverse of this function. You can write as in word f is inverse of f inverse, means f, this function is inverse of this function. You can write as f inverse inverse is equals to f. Now hence